It is the final day of exam prep review. Things that you want to get out before you get started is exam prep day 4 sheet. Hopefully you've already taken a stab at how to do these, but for those of you who need some guidance, this video should be your solution. Other things, if you're not doing them, if you haven't done them yet for the first time, you'll want your calculator. And some test taking tools that'll be relevant for this section are the heat test taking tool, which has a Q equals MC delta T round little buddy. It also has phase change information with a graph on it, and even an example of how the phase changes need to be done. For the other side, you will need some gas law test taking tool information that has combined gas law as well as some Pov-Nert gas laws. So now that we have those all ready, it's time to get started. The first one is a heat question. The specific heat of glass is 0.50 joules per gram degree Celsius. How many joules of heat are required to raise the temp of a 56 gram chunk of glass from 15 to 90? So I'm after how much heat. That's what I cover up on the round little buddy. Heat, when I cover that up, tells me I just take the mass times the specific heat times the delta T, which is change in temperature. The mass is 56 grams. The specific heat of glass is 0.50 joules per gram degree Celsius. And the change of temperature from 15 to 90 minus 15 is 75 degrees Celsius. These type do not need to be in Kelvin. Gas law ones do need to be in Kelvin. 56 times 0.5 times 75 is a change of 2100. 2100. It's got to be a unit of heat. Sometimes it's in calories, sometimes in joules. This specific heat tells us that it's going to be joules because grams and grams, degrees Celsius, all cross out 2100 joules. A certain substance, apparently we're trying to figure that out, with a mass of 150 grams, is heated from 50 to 100. It absorbs 1050 joules of heat. Calculate the specific heat of the substance and identify it using the following table. So what I need to do on this one is figure out a specific heat. And if I cover up the C, or the specific heat symbol, I put Q, which is heat, on top, and mass and change in temperature on the bottom. 150 grams. No, that's not what I want. I need the heat. 1050 joules on top, the mass 150 grams, and the change in temperature from 50 to 100. That's a change of 50. 100 minus 50 is 50 degrees Celsius. I'm not a parenthesis user, so I'll put in 1050 divided by 150 and also divided by 50 would be 0.14 joules over grams degrees Celsius, clearly making that mercury. I circle mercury as my correct answer. Next section, you'll see the word enthalpy. We've used the term heat more than enthalpy, but enthalpy changes are just heat changes. So we're calculating enthalpy changes that occur during a warming or cooling curve. We've had warming and cooling curves. They're not really curvy, they're more like straight lines. That what happens if you heat up some frozen water? It'll warm up, then it'll melt with no temperature change, then it'll warm up some more, then it'll evaporate with no temperature change, then it'll warm up some more. We can keep track of how much heat is needed to either warm things up and melt them, or cool them off, make them condense, make them freeze. So let's see what we're needing to deal with on this first one. How much heat is absorbed when 25 grams of ice is converted to steam at 115? So if we're dealing with ice and we need to get it to steam, if I'm checking this, it's going to be a 1, 2, 3, 4, 5-step problem. Another way of looking at that is if I'm starting with negative 11 with water and I'm going to 115, negative 11 would be somewhere in here, but I'd still go through the same things. How many segments do I go through? 1, 2, 3, 4, 5 different segments. So I know that I'm going to have 5 different segments. I also know that I'm dealing with 25 grams each time. So I'm going to write 25 grams, 25 grams, 25 grams. I'm going to skip over where I have more room. 25 grams and 25 grams. I'm going to have 5 different segments that I'm going to have to add up all the heat for each one of those. There's an example of a 5-step problem on the back, so you do have a guide to help you that's showing you pretty much what's happening with this type. When we warm up ice, melt it, warm up water, evaporate it, and warm up steam some more. So I'm going to set it up very similar to this one. Rather than just copying these numbers though, I'm going to try to understand where I'm getting these numbers from the test. So the first one says 25 grams of ice at -11. So I'm needing a change in temperature. It's got to be first warmed up to the point where it melts. So the first part is an MC delta T part. So a change in temperature for this part. That's going to be heat of, it's just an MC delta T. 25 grams times specific heat of ice is 2.09 joules per gram degree Celsius times the change in temperature. This problem starts at -11, but it's only going to heat up to 0 before it melts, so the change is going to be 11 degrees Celsius. Let's see if it looks very similar. It does. It looks similar to our guide on the back. One thing we're going to need to do though, since this was joules, we're going to need to have it in kilojoules, because when we add them all together, we're going to want to know our heat in kilojoules, because it says how much heat in kilojoules. So I'm going to add a times 1/1000 step. The first, the third, and the fifth segments are all MC delta T's, so I might as well just set those all up first. That's how I'm going to choose to do it. The next one is 25 grams times, to get from 0, this is just a change in temperature of liquid water. So liquid water's specific heat is 4.184 joules per gram 4.184 joules per gram degree Celsius, and it's going to need to change 100 degrees before it can start to evaporate. So this will be 100 degrees Celsius as my change in temp. Since again that's in joules, I'm going to multiply by 1/1000, and because 1 kilojoule is 1,000 joules, 1 kilojoule is 1,000 joules up there. So that one is set up. There's going to be one more MC delta T part. The last segment is when the water changes from steam, from when it was first evaporated at 100 to 115 degrees Celsius. So that's a change of 15. 25 times specific heat of gaseous water is 1.84 joules per gram degree Celsius times the change in temp from 100 to 115 will be a change of 15 degrees Celsius. I got those 3 set up. They look very similar using specific heats like 2.09, 4.184, and 1.84, and it'll be in kilojoules each of these. (25) times 2.09 times 11 divided by 1,000 . 25 times 4.184 times 100 divided by 1,000. I'm seeing a big discrepancy between this number and this number, so I'm turning my brain on and asking myself, why is there so much more heat required? I'm going to redo this one up here. Confident that I did the right thing on this. And so probably because this is such a bigger change, 100 degrees Celsius, it's going to require more energy, plus the specific heat is much higher. So it is making sense. Finally, the last section, 25 times 4.184, clear. 25 times 1.84 times 15 divided by 1,000 equals 0.69 kilojoules. The next two are, the other two that I haven't done yet are the ones that have to do with melting and also evaporating. The melting portion of it and the evaporating, we have to consult the heat of vaporization and the heat of fusion. They are written on this side. The heat of vaporization for water is 40.7 kilojoules per mole. We'll have to deal with that mole. And the heat of fusion for liquid, when we're melting it, is 6.01 kilojoules per mole. It takes a lot less energy to melt something than it does to actually make them jump out of the container and make them actually evaporate. So how many grams do we have? We have 25 grams. When we're melting it, the heat of fusion is 6.01 kilojoules per mole. But this isn't in moles, this is in grams. It's H2O, and 1 mole of water is 18 grams. So if we say that, if we multiply that, if we acknowledge that 1 mole is 18 grams, much the same way it did on the back, we'll have that one set up correct. 25 times 6.01 divided by 18, because it's on the bottom, 8.34 kilojoules. And finally, the last section, 25. We're going to need the heat of vaporization for water, which is 40.7 kilojoules per mole. We have to multiply it by the fact that 1 mole is 18 grams, or in essence divide by 18 grams. 25 times 40.7 divided by 18. And the largest amount of energy is going to take to actually evaporate this, 56.5 kilojoules. I'm not done yet. How much heat? I now have to add up 0.57 plus 8.34 plus 10.46 plus 56.5 plus 0.69, and I end up with 76.7 kilojoules approximately.